Hello everyone. In this video, we are going to compare two different approaches for building machine learning pipeline, a traditional monolithic workflow and a modular DVC based pipeline. In software engineering, Git solves version control very effectively because applications mainly depends on a source code. But in machine learning, a model depends on much more than code. A model is a combination of code, data, and the hyperparameters. Even a small change in the data or the parameters can completely change the model's output. Why traditional ML workflow fails? Most beginners start with Jupyter Notebook or large Python scripts. Initially, this works fine, but after a few weeks, problems begins. For example, a teammate may ask, "How did you achieve 92% accuracy?" And suddenly nobody remembers which data version used, which dataset version we are used, which pre-processing steps were applied, or which hyperparameters were selected. This is where DVC, data version control, becomes extremely important. DVC works like Git, but for datasets and machine learning artifacts. It helps us version datasets, track models, reproduce experiments, and effectively. Before building ML pipelines, we first need to solve the famous problem. It works on my machine. Different operating systems and library versions can completely break down reproducibility. We are using a lightweight Python image to reduce the image size and improve the build speed. Here, we install Git because DVC internal depends on Git repositories. This installs all required machine learning and DVC libraries. And then we go to requirements.txt. DVC supports multiple remote storage systems like AWS S3, Azure, SSH, and Google Drive. So in this project, we are using Google Drive as the remote storage. The volume mapping connects my local project folder with the Docker container, so I can edit the code locally while executing everything inside the Docker containers. The entire machine learning pipeline is implemented inside a single Python file. First, we load the adult income dataset using pandas and then data cleaning. Next, we clean the missing values and remove the invalid records. Feature encoding. So in label encoding, machine learning model cannot understand the text directly, so we convert categorical values into numerical representation. Then we train using a random forest classifier on the processed dataset. Finally, we evaluate the matrix using accuracy, AUC, and F1 macro score. Now we will run the script. Now we'll go to the project location, open the command prompt, run the command. After it's done, these are the final performance metrics generated by the pipeline. Now imagine this dataset is 50 gigabytes and the pre-processing takes 20 minutes. If I only change one hyperparameter, like for example, estimators from 100 that are changed to 150, the entire pipeline runs again. That means loading data again, cleaning again, encoding, training again and again. This wastes enormous compute time. And this is when the DVC pipeline architecture comes into the time. Instead of one giant script, we split the workflow into multiple stages. Prepare.py, this stage handles the raw data, cleaning, and creates a clean canonical dataset. This step converts clean data into a machine learning ready features. This stage is responsible for only for the model training, and this stage calculates the performance metrics. All configurable values are stored in one centralized configuration line. This removes hard-coded values from the source code. The dvc.yaml file defines the entire machine learning pipeline as a directed acyclic graph. Let's see the dependencies. DVC monitors these dependencies using a constant hashing. If the parameter changes, DVC marks the training stage as outdated. And this output is we can see here. DVC will automatically execute the pipeline based on dependencies. Stage prepare didn't change, skipping. Stage featureize didn't change, skipping. This is the biggest advantage of the modular pipeline. DVC understands the pre-processing has already been completed, so it skips unnecessary computation and restrains only the model. This dramatically speeds up experimentation. And the next step would be experiment tracking. DVC provides a lightweight experiment management. We can run multiple experiments without manually tracking configurations. Here we can compare parameters, accuracy, and F1 scores. Shallow trees may underfit the data, very deep trees may overfit. DVC helps us systematically compare these experiments. Large datasets are models are stored remotely in Google Drive. GitHub only stores the lightweight tracking files. When another developer clones the repository, they simply run DVC pull and DVC downloads the exact datasets and models needed to reproduce the work. Here we can clearly observe the performance improvement achieved through DVC caching. When does DVC becomes worth it? DVC introduces us some initial setup overhead. We need modular scripts, YAML configuration, and a pipeline definition. But during large scale experimentation, this overhead becomes extremely valuable. Monolithic pipelines may work for small experiment, but scalable machine learning systems require reproducibility, modularity. collaboration, and intelligent caching, and DVC provides exact those capabilities. Thank you so much. Thank you so much for watching. I hope this video helped you understand the practical advantages of modular DVC and pipeline over traditional monolithic workflows. Please check the GitHub repository for the complete implementation. Thank you.